With gases, we're always having to specify the temperature and the pressure, which is something we don't have to do with solids, liquids, and aqueous solutions. So just to kind of have a common reference point, like sea level is a common reference for altitude. We have something called standard temperature and pressure, which is abbreviated STP. And so standard pressure is 1 atmosphere of pressure. It's like normal, right? Normal pressure. So 1 atmosphere, which is the same as 760 torr or 760 millimeters of mercury. Standard pressure is 0 degrees Celsius or 273 Kelvin. And you might think, well, why do they use 0? Why not use room temperature? A lot of times 25 degrees Celsius is used as kind of a standard temperature. But 0 degrees Celsius is the temperature of an ice water bath. And so even if you don't have a thermometer, even if you were doing these experiments back in the 1600s, if you wanted to know the temperature of your gas, if you put it in ice water, it's going to be 0 degrees Celsius. So that's my personal way of remembering what standard temperature is. It's something that's easy to obtain. So 0 Celsius, 1 atmosphere. STP is useful for making comparisons between gases, because if both gases are at STP, then we can look at the volume and the moles instead of having to specify everything. So we have something called a molar volume. So we've had molar mass, right? That was the mass of a mole. Molar volume is the volume of a mole. It's the volume of a mole of gas at STP. So we can calculate that using the ideal gas law. So we want to calculate the volume of 1 mole of gas. Whoops. So we're putting in 1 mole, exactly 1 mole, for the amount, and we've got the ideal gas constant. And we're going to use standard temperature, so 73 Kelvin, and standard pressure, 1 atmosphere. And we get 22.4 liters. So this is the volume of 1 mole of any gas at STP. And so this is a very useful conversion factor. The students sometimes get a little carried away. You can only use this with gases. So you can't use this as, with like carbon or something, or an aqueous solution. It's only for gases. So the molar volume of any gas at STP, 22.4 liters per mole. So 1 mole is 6.022 times 10 to the 23rd molecules of gas. It doesn't matter what the gas is, it's still going to occupy the same volume. And that's because there's so much empty space. So again, this is a very useful conversion factor for gases. Here we're looking at an illustration that's showing us 1 mole of helium gas at STP, 1 mole of xenon gas at STP, and 1 mole of methane gas at STP. They all occupy the same volume, 22.4 liters. They're not going to weigh the same. The xenon's going to be much heavier because each of these atoms weighs a lot more than either the helium atom or the methane molecule, but they're all going to take up the same amount of space. So this is kind of like that test question that everybody loves to hate on the previous exam about how many particles in the 10 grams. Which one has the most particles? Which of these gas samples has the greatest volume at STP? A gram of hydrogen, a gram of oxygen, or a gram of argon? So the volume depends on the number of particles, right? So we want to know which of these is going to give us the most particles. And that's going to be the one that has the heaviest atom or the lightest atom? The lightest. And so that would be the hydrogen. Right? Any questions about that? So we do talk about density when we do gases. And again, density is the ratio of the mass of a gas to its volume. We usually use the units grams per liter because gases are much less dense, and so using grams per liter gives us more reasonably sized numbers. We can calculate the density fairly simply if we say, well, let's take 1 mole of gas, and the mass of that is the molar mass, right? And the volume of 1 mole of gas at STP is 22.4 liters. So we can take the molar mass and divide by the molar volume and get the density of a gas at STP. So this is saying calculate the densities of helium and nitrogen at STP. So the density for helium will be the mass of 1 mole of helium, 4.003 grams, divided by the volume of 1 mole of helium, which is 22.4 liters. And so the 3 sig figs ends up 0.179. The density of nitrogen, so here helium and nitrogen, we're talking about them as elements. Is helium a diatomic element?
Mm-hmm. No.
No. Is nitrogen a diatomic element?
Yes.
Yes, it is. So then when I'm talking about its molar mass, I need to use N2. And so that's 28.02 grams instead of 14.01 divided by the volume. So that's going to be 1.25 grams per liter.
So when we do density for anything else, it's grams over milliliters except for gas. Then it's grams over liters.
So when we're doing liquids, it's grams per milliliter. For solids, they often use grams per cubic centimeter, but cubic centimeter and milliliter are the same thing, right? So for gases, it's usually grams per liter, because otherwise this would be 0.000179 grams per milliliter. So the air is mostly nitrogen. So at STP, the density of air is going to be close to 1.25 grams per liter. The density of helium is much less, which is why helium balloons will float in the air. We can also calculate gas density under other conditions. And again, when we're calculating density, that's the one time we can use the density equation. We're looking at the mass of a thing divided by its volume. So, we can find the volume of the gas using the gas law, ideal gas law. If no quantity is given, then we'll choose to use 1 mole of gas. So the density is directly proportional to the molar mass, and this is an equation that you have in this book. In the book, the density is the pressure times the molar mass divided by RT, and there's nothing wrong with that equation, but it's another equation you have to remember, and I'm not going to give you that equation on an exam. I think it's better to just think of the density equation. Well, I need to find the mass and divide by the volume, and here's my density. Fewer equations to remember. So that's how I'm going to do my examples. So calculate the density of xenon gas at a pressure of 742 millimeters of mercury and a temperature of 45 degrees Celsius. So 742 millimeters of mercury, 45 degrees Celsius, and we want the density. Now, this isn't a number, but it is a piece of information that we need. We're talking about xenon. So we're trying to find the density. Density is mass divided by volume. And then we've got some information here, some numbers, 742 millimeters of mercury and 45 degrees Celsius. So the millimeters of mercury, that's my pressure, and this is a temperature. So I need the mass of this and the volume. Does the density of xenon gas change if you have more or less gas under the same conditions? Does the density of a log change if you cut it in half? No, because the mass and the volume are changing in the same way, and so the density is constant. And so they didn't tell us how big the sample is because it doesn't matter. But if we want to calculate the mass, then we need to have a sample amount, right? So we get to choose whatever we want, so we might as well make it easy. Let's choose 1 mole. So if I have 1 mole of xenon, so we're just choosing 1 mole, choose n equals 1. What is the mass of 1 mole of xenon gas? It's up on the periodic table, right? 131.3. 131.3 grams. That's the molar mass of xenon, that's the mass of 1 mole. What's the volume of this gas? Well, we have the information we need to calculate it using the ideal gas law. Volume equals nRT over P. So we chose 1 mole, and we need R, right? 0.08206 liter atmospheres per mole Kelvin. And then we need the temperature. Can we use degrees Celsius? No, we can't. We have to convert this. So the temperature in kelvins is 318. So 318 Kelvin. And then we'll divide by the pressure. Can we use millimeters of mercury? No, we can't. The solution seems kind of messy, a lot of steps, but using that other equation is not going to be much simpler, but it definitely works. Any other questions? Okay, this one's a little different. The density of a gas is 1.43 grams per liter at a temperature of 23 degrees Celsius and a pressure of 0.789 atmospheres. Calculate the molar mass of the gas. So I'm given a density, a temperature, a pressure, and I'm looking for the molar mass. Again, you could use that equation, but like I said, my brain just does not remember that. So I would look at this problem and say, they want the molar mass. Well, what is molar mass? Molar mass equals the mass in grams divided by the number of moles, right? So I'm given a couple of things here. I'm given 1.43 grams per liter. That's the density. I'm given a pressure of 0.789 atmospheres. Oh, and I skipped the temperature. Temperature of 23 degrees Celsius. Does the molar mass depend on, does it change if I change the sample size? No. Because again, I don't know how much of this gas there is, but I don't need to know. So I can choose an amount that'll make my calculations easier. You could choose 1 mole of gas. I'm going to choose 1 liter of gas. Because if I have 1 liter of gas, then I can very easily find its mass, right? So I'm just going to choose 1 liter of gas. So 1 liter, I'm going to use the density to calculate the mass. So the mass is 1.43 grams. And now I need to find the moles. So we're going to use the ideal gas law for that. So the number of moles is equal to the pressure times the volume divided by R times the temperature. So they gave me the pressure in atmospheres, so that was kind of nice of them. They didn't give me the volume, but what volume did I pick? 1 liter. I picked exactly 1 liter. And then we're going to divide by R, 0.08206 liter atmospheres per mole Kelvin. And the temperature. Can't use Celsius. So that's 296 Kelvin. Here we're dividing by 2 numbers, and so you need to be careful. A common mistake I see students do is they'll take 0.789 times 1 and divide by this times that. And I totally understand why your brain wants to do that. But then we need to be careful and put parentheses around this if you're going to use a multiply sign there. Otherwise, you're going to end up with a wildly incorrect answer. 0.789 times 1 divided by the quantity 0.08206 times 296. Let's see, this 0.032483 moles. 40.43 divided by that. No, 44.0 grams per mole is the molar mass of this gas. There's a reason we didn't start with this chapter first. Question? How can you tell if your molar mass is reasonable? Let's think about what would be an unreasonable molar mass. What if I got -4? No, you can't have a negative molar mass. What if I got 0.4 grams per mole? No, that's smaller than hydrogen, right? Hydrogen is 1 gram per mole, so your molar mass should never be less than 1. What if I got 52 gazillion? That'd be pretty suspicious. What if I got 543? There are larger molecules, so that's not impossible. Arrange the following gases in order of increasing density at STP. We're looking at neon, chlorine, fluorine, and oxygen. So density is mass divided by volume. If we had like 1 mole of each of these gases, they would occupy the same volume, right? So what we're really looking for here is the gas with the highest molar mass to be the most dense, right? So we've got neon is 20, chlorine is 35 times 2, fluorine is 19 times 2, and oxygen is 16 times 2, which is 32. This is a common type of exam question where we ask you to put something in order, and some students get them like mixed up. So in order of increasing means that I'm going to start with the little one and increase as I go down the list and get to the big one. Here the choices have the greater than, less than type sign, and so the small pointy end of this symbol is on the small side, and the big fat end is on the big side, okay, in case you don't remember how that worked from whenever they taught you that. So this is saying that neon is the smallest, then oxygen, then fluorine, then chlorine. Well, it might be helpful to actually just write the numbers down instead of trying to keep them in our heads, right? So neon was 20, chlorine was 2 times 35, so about 70. Fluorine was 2 times 19, so about 38. And oxygen, 2 times 16, so about 32. So neon is going to be the least dense, followed by oxygen, fluorine, and chlorine. So neon, oxygen, fluorine, chlorine. Okay? We can determine the molar mass of a gas experimentally, and we're going to do this in experiment 6A. So we can take a volatile liquid, and volatile just means that it evaporates easily at a fairly low temperature. we can heat this volatile liquid until it becomes a gas. We can measure the temperature, the pressure, and the volume of this gas. And then we can calculate the moles using the ideal gas law. We allow the gas to condense back into a liquid, we weigh it to find the mass, and we take the mass and we divide by the number of moles. So a sample of gas has a mass of 827 milligrams. Its volume is 0.270 liters at a temperature of 88 degrees Celsius and a pressure of 975 millimeters of mercury. Find its molar mass. So we've got these numbers. We're looking for molar mass. I'm going to approach this problem very similarly to how I did the density problem. Well, and that other molar mass problem. I'm going to remind myself, what does molar mass mean? Well, it's the mass in grams divided by the number of moles. And so I've got a bunch of numbers here. Let's write those down. 827 milligrams, 0.270 liters, 88 degrees Celsius, and 975 millimeters of mercury. So I've got a volume, a temperature, and a pressure. And this is the mass, right? So molar mass, I need the mass in grams divided by moles. Well, I've got the mass in milligrams. So we could do this. We could write 827 times 10 to the minus 3 grams, because milli stands for 10 to the minus 3. And then I need to find the moles using the ideal gas law. Are my units all good? No. The volume is fine in liters, but the temperature needs to be in Kelvin. So that's 361 Kelvin. And the pressure needs to be in atmospheres. So if I rearrange the ideal gas law to get moles is equal to the pressure times the volume divided by R times the temperature. So pressure 1.2829 atmospheres times the volume 0.270 liters, 0.08206 liter atmospheres per mole Kelvin, and my temperature of 361. Again, be careful entering this in your calculator. So 1.2829 times 0.270 divided by parentheses 0.08206 times 361, close the parentheses, press equals. So I'm getting N is equal to 0.011693 moles. Did I do that wrong? Let me try it again. Nope, I got the same answer. So the moles, 0.011693 moles. So 827 times 10 to the minus 3 divided by 0.011693. Is 70.7 grams per mole. Any questions? What's your calculator, Mr. David?
Yeah, I got something wrong.
Let me see. So it's 0.08206. Yep.
Thank you.
Off by a factor of 10, because just lost a 0. So here's an example that is more like the data we'll end up with from an experiment. An organic chemist isolates a colorless liquid from a petroleum sample. She places the liquid in a pre-weighed flask and puts the flask in boiling water, which vaporizes the liquid and fills the flask with gas. She closes the flask and re-weighs it. Her data is given below. Calculate the molar mass of the liquid. So we need the molar mass. I'm not going to highlight all of that because it's just all right there. So we think, well, molar mass is the mass divided by the number of moles. So those are the two things I need to find. Here I have the mass of the empty flask and the mass of the flask with gas in it. How do I find the mass of the gas? I'll subtract them. So I got 78.416 grams minus 77.834 grams. .582 grams. So that's the mass of this gas sample. And then I'm going to use the ideal gas law to calculate the moles. And these are the kind of units that the measuring devices have, but we need different units, don't we? We need our volume in liters. Well, that's not too bad. 213 times 10 to the minus 3 liters. We need our temperature in kelvins. Now this temperature was measured more precisely, 100.0. So I want to use 273.15 for this one. I end up with 373.15 kelvins. And then torr, remember torr is the same as millimeters of mercury. So 1 atmosphere is 760 torr. So I can put these numbers in here. Pressure 0.99211 atmospheres. The volume 213 times 10 to the minus 3 liters. Divided by Ideal gas law, gas constant, sorry. And the temperature, 373.15 Kelvin. Another way to do this on your calculator is if your calculator has a button that'll show you a fraction, then you can type this in to your calculator just like it looks, and then you don't have to worry about it. Yeah?
So the unit conversion from torr to atmosphere is the same as millimeter
Yes.
of mercury?
Yeah, torr and millimeters of mercury are two different names for the same thing. Yeah, exactly the same thing. So for my moles, I'm getting 0.0069012 moles. So I'm going to plug that in up here. .3 grams per mole. Any questions? So these kind of end up being sort of a critical thinking problem also. Scott, we have all these little pieces, and we need to figure out how we can put them together, how we can stack the blocks up to get what we need, right? So we need to practice the individual pieces first, and then we can practice putting them together. Oh look, we made it all the way through that section. Yay us.